Hello, everyone. My name is Jack Foreman, and I would like to briefly discuss with you how we can combat climate change. Extreme ways of combating climate change is with green energy. Here on the left, we see a infographic made by the EPA showing conventional versus green energy power sources. Each is deemed less and more beneficial, respectively. In the conventional power, we see our traditional energy sources like coal, oil, and natural gas, and we also see nuclear over here, which is very interesting. On the green power side, we see wind, solar, and biomass. On the right side of this diagram, we see grams of CO2 equivalent produced per kilowatt hour of energy produced. So, unsurprisingly, we see coal on the far hand left side of this equation, producing some of the most CO2. But next to it, we see biomass, which is very interesting because it's deemed a green power source. On the right hand side of this, we see nuclear with some of the lowest CO2 equivalents per kilowatt hour of energy produced. And so, why aren't we using this very CO2 reduced process instead of our other green power sources? Well, and what is nuclear energy? So, nuclear energy comes in two forms: fission and fusion. Fusion is what's done on the sun and in the center of stars, where two lighter elements is joined together to make one heavier one. This is one of the most important processes in the universe because it's the reason that all elements beyond hydrogen exist, and is the reason that all life here on Earth exists. Fission, on the other hand, is what we do here on Earth. It involves splitting a larger atom into two smaller ones, and in the process, releasing energy. So, how do we access this? So, this is a coal plant where coal is shoveled into a boiler, which heats up steam or heats water into steam, which then turns a turbine, which then turns a generator, which produces electricity. Then the water is then condensed and it's brought back around through the cycle. Similar to in a coal plant, we see the similar process of steam being water being boiled and turned into steam, driving a turbine, which drives a generator, which produces electricity. The only real difference is where does that energy come from? More specifically, energy is released through that process of fission, which drives this whole reaction. So, most of our energy currently come from? Well, unsurprisingly, it comes from primarily petroleum, natural gas, and coal, which all follow similar processes as previously shown. It also shows nuclear over here producing 8% of our power and renewable energy producing 12% of our power. So, how much money are we currently investing into these two different energy sources? Because they need to be investigated so that we can have the cheapest option for combating climate change. So, over here on the right, we see the current investment in renewable energies dramatically increasing over the years. In comparison, nuclear has remained relatively low. However, on the previous slide, we saw that they produce very similar amounts of energy with 8% to 12%. So why aren't we using a cheaper, greener energy source over our traditional green energy sources? Well, the main reason for that is because of two reasons. One being nuclear disasters, and the other being nuclear waste. So first, we'll go into one of the most famous nuclear reaction disasters that has ever occurred, primarily being Chernobyl. Chernobyl occurred. To understand why Chernobyl occurred, we need to look at more into what is actually happening during nuclear reactions. So first, a neutron comes in and it hits a uranium atom. And then this splits into two lighter elements, and then it splits on average into 2.5 neutrons. These neutrons then can go find their own uranium atoms and cause these to go split, releasing another 2.5 neutrons per reaction. This can very quickly run into a runaway reaction where more and more energy is produced, which can lead to an explosion. This is a balancing act between two different concepts. One is neutron absorbers and one is neutron moderators. First, we'll go into absorbers. So xenon is a neutron absorber where it takes these excess neutrons that would normally go try and find another uranium atom, and they get absorbed by this xenon atom, stopping them from continuing the reaction downstream. This is what I would deem as the brakes of the reaction, and it slows down the reaction rate. On the other hand, we have the accelerator, which is neutron moderators. So in a weird way, slow-moving neutrons can actually cause fission and the reaction to continue. Fast-moving neutrons cannot. They will not fizz. Fizz? Yes, fizz. So what we need to do is slow down the neutrons. And so we introduce these neutron moderators to slow down the neutrons and allow them to fizz with other atoms. So it is a very delicate balancing act between these two ideas. To understand what happened at Chernobyl, we need to understand control rods. So control rods are a very important process that allow us to directly control how nuclear reactors react. So the primary body of a control rod consists of boron, which is a neutron absorber. So it slows down the reaction. So whenever this red section is in the reactor, it slows down. On the other hand, there were these graphite tips on the end of these things. And I'll explain why they were there. But they were made of graphite, which is a neutron moderator, which speeds up the reaction. So these reactors, because of the price of heavy water, they used regular water. When they used regular water over heavy water, regular water acts as a neutron absorber, and heavy water acts as a neutron moderator. So because this reactor had a bunch of water sitting on it, it had a bunch of neutron absorbers. So in order to combat this and balance out the neutron absorbing, they had these graphite tips added to the end of the control rods so that when the control rods weren't inserted, it wasn't just replaced with water, which would slow down the reaction. They would actually have these graphite tips, which would speed up the reaction, which is the goal of withdrawing control rods. So what happened during the events on April 26, 1986? What ended up happening was they were going for a test. This test involved bringing the nuclear reactor to a very low setting. What ended up happening is at this very low setting, they spent an extended amount of time for various political reasons. While it was sitting at this lower energy state, xenon, which is another neutron absorber, was building up in the reactor. This element is normally burnt away at normal reaction rates. However, at this low power state, it was just building up inside the nuclear reactor, while it was sitting here with its boron rods partially inserted to slow down the reactor. As the xenon is building up, they finally say it's time for the test. And so they go to bring the power back up. And what ends up happening is that they pull these control rods completely out, almost all of them completely out. And while they're pulling them out, eventually they pull out enough and the reaction rate increases dramatically. And then in that second, all the xenon is burnt away. And then the reaction rate, we just lost another neutron absorber in this. So we have less neutron absorbers, and we have our graphite tips now completely in the reactor, which is a neutron moderator, which is speeding up the reaction. The only thing currently slowing down this reactor is the water in the reactor, which is another neutron absorber. However, they notice that there's a runaway reaction occurring because they have all the control rods pulled out and they have graphite accelerating the reaction and they have no xenon slowing down the reaction. So they hit this famous button called AZ5. And when they press it, it pushes all the control rods in to slow down the entire reactor. And while doing so, they were not able to compensate for this, but when they pushed the control rods in, they displaced the water here at the bottom of the reactor. This is a neutron absorber, and with it being gone, and all these control rods being pushed down at the same time, the bottom of this reactor very quickly increased in reactivity. And then this part of the reactor, something broke, and the control rods were locked in place, causing a runaway reaction, which led to the explosion that occurred. This event was due to a multitude of reasons politically, but engineerily speaking, this flaw was well known at the time, and it needed to be expressed because many people knew about it. Here in the United States at the time, this flaw was well known. We did not have it in our reactors, and this event could not have occurred here in the United States. It was also well known in the Soviet Union at the time. However, it was not fixed due to costs of upgrading these reactors to modern reactors at the time. Famous nuclear incidents was Fukushima. What happened there was a earthquake made a massive tsunami that ended up breaking over the flood walls and flooding the nuclear reactor, putting their backup generators and power offline, which led to a nuclear meltdown. Um, this flaw, again, was well known at the time. This height here was well under the design specifications. It was, in fact, most designs are typically made to prevent what is called the 100 years flood, which is the maximum height you can expect water to go in 100 years. And it was well below that limit. It was well documented before the event occurred. And not surprisingly, when the 100 years flood occurred, it flooded the reactor because the walls were not high enough. So one of the things that we need to address when talking about nuclear reactors is nuclear waste. Nuclear waste is a big deal because it can last millions of years. However, in Finland, they've made a burial tomb for nuclear waste where they will be able to hold all the nuclear waste that Finland generates for the next 100 years, and they will be able to safely store it for the next 100,000 years. It will not be accessed for humans for that entire time and will be a safe place for it to decay without hurting anyone. So, in conclusion, evaluating nuclear energy is a very important process to be able to combat climate change. It is a possibly a cheap, very green energy source that should be evaluated more to combat climate change more effectively. If you'd like to learn more, this slide shows my sources, and there are plenty of tools online for further learning. Oh,